Yeah, she had a, as I recall, Titanic-themed wedding.
Whoa.
That, now that was, this was a long time ago, like before you guys were born, I believe. But I don't know. There's the term cringe had not been invented at that point, but if it had, anyway. All right, I will find my laser so we can get started. Oh, there it is. All right. Let me begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and just ask that you guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. So, sorry to the poor soul who's out for the wedding. Just say that. All right, so this is my lecture 18. We've already gone through all this stuff. I don't think there's anything new much to see here. No, we worked all this out before. Right? This nothing new there. I'm going to post these, of course. And I think this, for the most part, we already worked through as well. This is last class. The one new thing here that I just, since I'm using this projector, I might as well use it. This is the so-called Dirac string potential. This is another attack on the the vector potential for the magnetic monopole. You can write it like this. I don't know how Dirac came up with this formula, but it's quite beautiful. And its curl gives you the Coulomb field. But, obviously it's got a singularity manifestly at, R equals to Z. So that's the so-called Dirac string. And if you want to read more about that, I would encourage you to look at section 1.9 of Geometry, Topology, and Physics by Mikio Nakahara, which is an amazingly deep text that is used at a lot of good schools. It's kind of a mathematical physics course. It gets all the way through like bosonic string theory. It's a pretty intense book. We talked about the Aronoff-Bohm effect. I'm saying that wrong. Dr. Budara corrected me when I said it. But I'm going to keep saying Aronoff-Bohm effect. I think I'm collapsing a syllable in there somewhere. But we went through this argument in class. Here it is again, written out. All right, great. So that brings us to today, which is lecture number 20. And so it's a grab bag of things. One of these things we already did a little bit last class, which was talk about boundary conditions, but I wanted to do it again. So is it possible to choose a vector potential for which the magnetic fields, the curl of the vector potential and the divergence is zero? So we've claimed that we can do this. The reason the reason that we can is actually kind of cool, because if you started with an arbitrary, vector potential here, like A naught, right? Then, well, of course, if the divergence of A naught is zero, then we're done, right? If it's not, then we can add a gradient to it, and that doesn't change the magnetic field because, of course, the curl of the gradient is zero. And then if you look at what that does, then the divergence of A is this, right? And if we want to have the divergence of A be zero, then we just simply need to have the Laplacian of this lambda we're adding be equal to minus the divergence. But hey, that's just Poisson's equation, so we can solve it, basically. We can just solve it by the usual means that we solve Poisson's equation, namely to formulate the solution as the integral of, the divergence divided by the separation distance integrated over the volume over which it's non-zero. And that would create then a vector potential which has zero divergence. So it's not crazy to go looking for one. It's not at all an imposition to enforce the so-called Coulomb gauge. And then I'm like, okay, so practically speaking though, what that, having the Coulomb gauge, having the divergence of the vector potential be zero means that when we take the curl of the curl, we get back, minus the Laplacian squared A is equal to mu naught times the current density. And so it seems to me that if we just calculate this, we're probably going to I was thinking, well, if I just calculate this, then I'm already going to be in the Coulomb gauge, right? But let's think about that. I don't think that's necessarily the case, though, because this could be 0 even when the divergence of A was what? We just need divergence of A as constant, right? If the divergence of A is constant, then this gradient's to 0, you know? And so 0 is a special choice of that constant, which is most beautiful. So I know, I'm not entirely sure that doing this integral necessarily puts you in the Coulomb gauge, is all I'm saying. All right, so to check that you're in the Coulomb gauge, I would, you know, generally speaking, feel like you need to actually check on the divergence. I think all the examples we've worked are in the Coulomb gauge, though. So later, much later in this course, we'll talk about something called the Lorentz gauge, which is a different gauge choice, which is more simpatico with like relativistic considerations. But anyway, first things first, we work with magnetostatics. So, and here's just like the big picture of magnetostatics. We have vector potential, magnetic field, current density. And so to get from here to here, we do this integral. To get from there to there, we take the Laplacian of A. That gives us, you divide it by minus mu naught. There you got the current density, right? That makes a super nice test question, right? I just give you A and say, find the current density. That seems like a really hard question unless you know this, you know, in which case it's just kind of a dumb question. But that's the kind of question I ask, right? So anyway, sometimes. And then, of course, this is our beloved Biot-Savart law, which is in some sense basic in all this story. And then, of course, here's Ampere's law going back the other way, like the curl of B. And then Griffiths lumps in the divergence of B being 0 and the Coulomb gauge into this picture, but I don't feel like they belong there, so I took them out. Because like the divergence being 0 doesn't really fit together with the other things there, I don't think. Of course, no magnetic monopoles is a thing, right? Now, so the boundary conditions for the magnetic field we should think about, right? And so there's two things, just like with the electric field, we thought about a surface. We thought about like a little pillbox close above and below the surface, right? And so defining that as above, perpendicular below, we're going to have, you know, oh man, I was going to do times an area here, and I forgot. So of course the flux is like the area times B perpendicular above minus B perpendicular below times the area. Then we divide both sides by the area, and we get this. All right, but you guys know. So anyway, we get that the perpendicular field above and below the surface, even when there's a current density, K, it's going to be equal just applying the no magnetic monopoles rule and the divergence theorem to a little box. If we look a little Amperian loop, then the current, which is flowing through there, is simply K times L, and of course times mu naught. That's Ampere's law. And on the flip side, we have the circulation's positive up here, but negative down there, because of course we're defining the parallel direction the same above and below in order to make a comparison. I mean, if you really wanted to be perverse, you could say, well, the parallel direction up here is like this, but the parallel direction down there is the other way, you know? And then you'd have a plus instead of a minus here, but we don't do that because that would be weird and evil. So yes, we get this is the situation. So there's in the presence of a current, there is a difference in the above and below parallel magnetic field. And of course, we have to take that parallel direction to be perpendicular to the current to make this work, right? If the loop was, if it was at an angle to the current, then we'd have to account for that, So this is, of course, assuming that the parallel direction is perpendicular to the given current for this formula. And so to make that not, in general, then you can see that what we'd have is the difference in the magnetic fields is mu naught times the cross product of K with the normal. It's just that I've written K and the normal vector to be perpendicular in this example, but if you were to make the loop adjust, then that would add an angle in, then you'd account for that angle back in this formula. Anyway. If you're not content with my derivation, you could put the loop at an angle and work it out. Let's see here. So then, what about the vector potential? Well, the vector potential if we're working with a Coulomb condition, then we can again use the little, little flux box there and make the width of it, like the height of the box, shrink to 0 if you like. So clearly the flux out the top is equal to the flux out the bottom, which ends up giving us perpendicular components above and below are equal. I just made it length L, width W, because I didn't want to use the area to be A in this particular case, because A, it's already an A here. So it forced me to do length and width. And then if I look at a little I say Amperian, but if I look at a little loop, it's not an Amperian loop because we're talking about the vector potential, right? But if you do that and apply Stokes' theorem, you've got the curl of A, like so, which is the magnetic field. And then Griffiths argues that this has to be 0 because he says, and I quote, "The flux through an Amperian loop of vanishing thickness is 0." This is page 3? 251 of Griffiths. But I'm thinking that if we just let the height of this shrink to 0, then there can't be a magnetic flux through it. I don't know. Well, the current's going this way. So, yeah, I don't know. I mean, this could be improved, I feel like. I'm not sure how exactly at the moment, but I'm not entirely happy about this argument. But anyway, it is true, nevertheless, that the vector potential is continuous. And then if we reformulate that in terms of cross products, we can see that B perpendicular above, as we argued before, B perpendicular above minus below is mu naught times the surface current across the normal to the surface. But that also has to be the difference of the curls of the vector potential above and below. But if you think through this, if we take the normal direction as one of the directions, right, then this is the direction, this is a direction of the curl, which is not the normal and not the k direction, which means it has to involve the normal derivative because the way the curl works. And so that, you could sort through it like that. But I think the other thing you could do is just go back to the previous page and look at the Amperian loop and just if we just go back to the Amperian loop of the previous page, we could derive it from that as well. Because basically just, here, let me go back. This thing here. So let's see here. I'm trying to think. I think we should, in principle, you can look at that loop and sort through this is equal to this is also equal to the integral of the flux of the curl through the loop. And if you look at that, because this is anyway, you could look at that and derive the result that I just had there. I'm going to go on. I have more to show you. So I was going to just do this example on the fly last class. I thought, we'll just do it. We'll just work it out in class. It's good that I didn't try. It wouldn't have gone well. So let's sit and enjoy this example for a few minutes. So we have a spherical shell of radius r. It carries a uniform surface charge sigma, and it's set spinning at angular velocity omega. Find the vector potential due to this current distribution at r. So the first thing Griffiths does is he does something a little bit sneaky. He does this in every problem that has difficult geometry. If you look at the book, this is not the first time he's done this. He did this before to find the the field due to the uniformly charged spherical shell before? He did the same thing. He put the field point on the z-axis. You know, because if you do that, then you can use the law of cosines in the picture, kind of like this. All right, but this particular problem also has the angular velocity that the thing is spinning at. So the second thing is done here, which is to put the field point on the z-axis, and without loss of generality, you can place the omega in the xz plane. All right, that's like a smart choice. You can see the picture. I've got the angles labeled in there. So we're trying to calculate the vector potential by integrating the surface current over this sphere. All right. Now, notice that the surface current is the surface density times the velocity. Now, have you guys talked about this in mechanics at all, like rigid body stuff at all? No. Okay. So if we have a rigid body, and you're going well, anyway, this is the tangential velocity, right? Because it's all of the charge is fixed in the sphere, and the sphere is just rotating, right? So that's just the tangential velocity, and we can calculate that from omega, because like v is, I think, omega cross r. We'll use that in a second here, but anyway, dA, of course, is what it usually is: r squared sine theta d phi prime d phi prime d theta prime d phi prime. And you see the distance between the source current and the field point is this script r, which is related to r prime and r in this triangle here. You see it? With angle theta prime. And so by law of cosines, we have the separation distance is this. All right, but then we need to calculate the velocity, all right? And so to find the velocity on a bit of the sphere that's rotating with angular velocity omega, we can use omega cross r prime, because we're imagining that the little bit that's spinning has velocity which is given according to that position vector on the sphere. All right. Now the whole sphere is spinning at that same angular velocity with respect to that axis. All right. But anyway. So this is just a general thing. Omega cross r prime gives me the tangential velocity for a rigid body with angular velocity omega and position vector r, assuming that that's with respect to the center of the sphere, of course. Anyway, so you calculate this cross product, right? So do you guys see why omega is what it is? So that's just plain old trigonometry. Since omega is this way, and that's angle psi, the x part of it is going to be sine psi, right? And the y part of it, rather the z part of it's, omega cosine psi, right? And then, oh man. Let me see if I can, there we go. Then, so then we calculate the cross product here. We get a bunch of terms, but if you look at the star, star, and star, these all have like, and then notice that we're taking these and we're putting them up here because we're integrating kv, sigma v, right? So let me go to the next line here. It's not as bad as it looks. It gets better. It gets better because you see, this when we put v into here, I didn't even write it out, but if you think about putting v into this integral, well, this piece, and this piece, they all integrate to 0 because you've just got an integral over d phi prime over the full 2 pi. And so like the sine phi prime, the cosine phi prime, and the sine phi prime over here, they just integrate to 0. The only thing you have otherwise is you got a sine theta prime, but that just integrates from 0 to pi because, that's how that angle goes to go over the whole sphere. So, despite the v looking kind of like formidable, only this piece actually matters. So that's kind of forgiving. And the sine psi is constant over the whole sphere, so we can pull it out of the integration. And lo and behold, we've got this minus 2, the r cubed sigma omega sine phi over 2. And then we just got to do this integral, right? And I looked at it, and it looked like it was just a u substitution. Well, one more step. So it looked like it was just a, make a u equals cosine substitution, and then it goes 1 and minus 1. Of course, Griffiths doesn't write this step down, but he goes straight to here, which is fine. That's a reasonable jump. I can see that. And then I'm like, oh, this is like just make a denominator substitution, right? I was like, and then I was like, wait, but it's not, wait a minute, there's a u here. What, how do I, it's not, no, it's not a u substitution. I mean, it is a u substitution, but what Griffiths doesn't show you is this. So w equals to the inside the square root, and then if I solve that for u, I have to plug that back into u. It's one of these kind of integrals. So I plug my u back into here, divided by the square. So I got, in terms of w. So I got this minus w, square root of w up here. You got this 2rr, and so that gives you a 4rr squared, r squared. And you got yourself a root w and a r squared plus r squared, root to the reciprocal root dw. You integrate that thing, you get this, and then you get that, and then you get this, and then you get that. The 2's, they be canceling. And finally, this is what Griffiths write down. Griffiths just writes this down. He just goes, this is the antiderivative. It is true that that's the antiderivative, but I feel like the reader is owed maybe a short calculation shows this is the antiderivative. I don't know, maybe that's warranted here. I don't know. This is actually not a hard integration. I'm just thinking slow this weekend, but anyway, I was very happy when I got done with it and I looked at this and I was like, that's what Griffiths wrote. Yay. We're not done. So then we put that into practice. So now we have an antiderivative for this. Yay. Fundamental theorem of calculus. Do the bounds. Take the difference. Yay. Well, that's a square root of a square. And that's a square root of a square. But this is a positive square. So that is actually just, they cancel, right? Over here, that could be positive or negative depending whether little r is bigger than or less than big R. In other words, whether you're inside the sphere or outside the sphere for your field point. That's interesting physically, the distinction. So we've got that and that. And so there are basically two formulas, either for outside or inside. You've got this or you got that. Now this, of course, simplifies like a lot. And here's how that goes. So there's probably a more clever way to do it. I just multiplied the stupid thing out and canceled. And after a bit, I saw this and that are the, in this Hunger Games of cancellation, this is the winner. And this is like the male winner, the female winner or something. They live happily ever after. In these two cases, I guess. I don't know. Whatever. I haven't watched the Hunger Games in a while. Man, it was a stupid movie, wasn't it? That was a really stupid movie. I know, I kind of like certain aspects of it, though. I don't know.
It was entertaining.
Yeah, it was entertaining, but I don't know. It's just kind of like, I guess I didn't completely hate the movie despite the fact that it had no likable character. So that's kind of something, I guess. Hamish? Which one's that? Is that the one played by the Woody? Is it Woody Harrelson's character? Yeah. Yes, I agree. That's right. He's the only likable character in that whole series.
What about the guy who makes the bread?
The guy who makes the bread?
Peta. Yeah, he's not that bad.
Peta? A guy named Peta makes bread? It's hilarious. That's some quality writing right there. Right? Yeah, okay. Sorry. I've never made a Hunger Games. What am I talking about? I have life experience to talk about this at all. Anyway, we should have more respect for people who read other people's words for money. But anyway, so let me continue reading Griffith's words here. But No, I worked this out. These are the strokes of my own pen. So there's some cancellation here. And after, I mean, wow, you know, it works out to just this? Yowzers. So, and then, so we found this formula. And of course, I've worked out that this inside the brackets is equal to that or that, depending which case you're in. And so if you convert that back using the fact that omega cross r is actually minus omega r sine phi y hat, then we can trade out the minus omega r sine phi y hat for an omega cross r, which is smart because now we've written our answer in a way which is geometric. And so we can divorce ourselves from Griffith's special setup of the field point. Now we have the formula written geometrically, which is really cool. This is like a very important trick. Choose a system of coordinates, work it out, and then rewrite it in terms of coordinate invariant, you know, ideas like cross products, dot products, right? So now we can reformulate our result with omega as pictured, as you might like to picture it, namely going in the z direction, like normal, because everybody, when they're given a charged spinning sphere, they of course put the direction of the angular velocity in the z direction. That's just natural. I mean, I'm partly joking, but no, I think that's natural. We have the nicest formulas for things spinning around the z-axis, right? If you think about it, this is like been our default in like classical mechanics as well, if you go back. Eventually, Dr. Budaris will start making stuff spin, and when he does, it's going to spin around the z-axis, I guarantee it. Maybe it will never happen. I don't know. We'll see. I should tell him to get to that on your test tomorrow. You know, you should always introduce new material on a test. Like, what's a test without new material, right?
I've never taken one of your tests I didn't learn from.
Thank you. Yes. I do try to. Anyway, I'll shut up. So anyway, there it is. The vector potential is such, but if we write it in terms of, you know, the spherical coordinate system like this, then, lo and behold, we can finally calculate the magnetic field from taking, I mean, so there's your vector potential. We calculated that, and it was relatively benign in terms of its structure, I guess. The curl, and we'll just look at the case that R is within R. In other words, in this case up here. Now there's, of course, 4 other terms in the curl, but those are irrelevant because those involve terms which are manifestly zero because we have no, you know, there is no theta hat, there is no r hat, so those terms are zero. So these are the only possible non-zero terms. And they are both non-zero because this gives you a sine squared, which differentiates to twice sine cosine. This is an r squared, which differentiates to 2r sine theta. Now the sine thetas over here, they'd be canceling. And that just leaves us with a cosine theta r hat minus sine theta theta hat. But this is actually z hat. And so, lo and behold, the magnetic field, if you have a charged sphere and it's spinning, right, around the z-axis, the magnetic field inside the sphere is uniform and upward. It's just a constant magnetic field inside that's proportional to 2/3 the permeability of free space times the radius of the sphere times the rate at which you're spinning times the surface charge density. Now this does assume that we have a uniform surface charge density, right? So if that wasn't the case, then all bets are off, right? You'd have to work it out however that would work for whatever other, I mean, if you're actually spinning at a high rate, right, and your charges are mobile, then it seems like the various, you know, centripetal forces and so forth might make the charge distribution not uniform, right? But if it really is a rigid body and they're stuck in place, then I think this makes sense. But I wonder if you tried to apply this idea to like a plasma or something where you don't really have a rigid body, you just had something that was swirling, it's obviously going to be like way more complicated, right?
Field also affects the charges.
The field affect the charges. Well, yes. So that we want a rigid body that they're glued in place, so not an issue. Yeah, so there it is. So yeah, I'm glad I didn't try to just like do that last class, because I don't think we would have gotten through it. Because there's a couple of steps in that example that are really devilish. That's a good example, though. It really is. It's a very good example. It's just not a good example for like a test question. I mean, that really should be like a homework question, honestly. I don't know. Anyway, now we've all seen it, so yay. We'll use it again today, though. So, the multipole expansion for magnetic fields, it rests upon the same mathematics, basically, that we already went through for the electrostatic case. And so, essentially, we looked at the binomial series for this thing, right? And after a little bit of math, we found this is what we found. All right, this is what we did. All right, in a nutshell. And so, if you think about a current loop like this, and we think about the separation distance, well, we again have the same. I mean, it's the same mathematics setting up the separation distance between source current segment, right? The source current segment and the field point. So we can calculate the multipole expansion for the vector potential in the same way we did for the scalar potential. You see, but you know, so this is like last class. I said we'd get back to this, is because I was hoping to get to this at the end of class. Didn't quite make it. Anyway, so this is the starting point. If we have a current loop, this is how to set up the vector potential, right? We integrate over the vector potential. Notice that this is like that dl. Oh, I wanted an L there. Oh man, that should be L, dl prime right there. Oh well. So then, this is my dl prime. We replace that with the expansion into Legendre polynomials, like so. All right, great. And then write out the first few. So the 0th term, remember P0 is just 1. So this just drops down to 1 over r times the integral of dl prime over the loop. And then next you got 1 over r squared integral over the loop of r prime cosine alpha dl prime, because P1 is cosine alpha, remember. P2 is 3/2 cosine squared alpha minus 1/2. Who could forget, right? That was, I mean, I know you guys you're already like yearning for us to return to the Legendre polynomials. You missed them already, I know. Well, I brought them back, so you're no longer. But now this right here is what? I mean, like I said, this integrates to 0. If you add dl prime all the way around a loop, what's the, you know, sum of the displacements around a loop is 0, right? Obviously. And so that's the monopole term. It integrates to 0. So the first term that contributes to the multipole expansion for the vector potential is the dipole. Then you could have the quadrupole, right? Now, so notice that the dipole field, we can pick a little bit more at that. So like, here's the definition. The dipole field is just the integral for a current loop. The dipole field contribution for a current loop is this integral around the current loop. And of course, we can rewrite that as like r hat dot r prime. Do you guys see that? So like alpha is the angle. We'd have to go back up to my picture, but alpha is the angle between r and r prime. So since that's the angle between r and r prime, well, wait, where's the magnitude of r hat? Well, it's a unit vector, right? So this is like just literally, this dot product is that, right? You guys with me? And then this is a homework problem earlier in Griffiths, which I don't know if I assigned you guys or not, but it's a fun one to go back and do. So like you can trade the integral of r hat over dot r prime over the loop for the integral of for minus r hat cross the area integral. So this is what this is gives you the so for a flat area, it's most easy to understand. It's just the area times the normal vector, right? I think if it was like a hemisphere or something, it's a little bit more funky, you know, maybe it would be like, I just don't, well, anyway, let me shut up about that. But this is nevertheless an exercise earlier in Griffiths that I should have assigned you guys if I didn't. And once you have that, then you can trade, you know, basically bring I into here. And then if you define, or if you do this, I times the integral of dA, that's the so-called dipole moment, all right? So the dipole moment in the case of, you know, the current going around so if the current like goes around the edge of an area, then I times the area vector, that's the dipole moment. So the dipole moment's like current times the area times the normal vector in the area. We'll do an example next that'll make this more clear. But anyway, this then simplifies to mu naught over 4 pi dipole moment cross r hat divided by r squared, which you maybe would recognize as being similar to the formula for the scalar potential for the dipole if we were to go back and look it up. Ow. Anyway, the r squared dependence there. Oh man, you gotta go. Dang it. Look, look, look. This is the end. Check it out. We go back to the charge sphere thing again, and we're able to use for a magnetic field with matter with magnetization the charged sphere example again, and we use the example again at the end of class. Anyway, you can see it. You watch later. You guys aren't going to leave, right? Okay. All right. 5:45. I had better be done in about 10 minutes, otherwise I'm not doing my job. So, all right. So, this is a nice example from Griffiths, like to find the dipole moment for a current loop. He gives us this kind of funky, like loop that goes like this, like that, right? The purple is the given loop, and so what you do is just add like a cross current in, and then that makes it two just plain old loops. All right. And so like number one, the normal is y hat, and like everything's w. So these are actually both squares, despite my picture. So the area vector for one is w squared y hat. The area vector for two is w squared z hat. You got to use the right-hand rule to ascribe the correct area direction, right? It's got to go like, your right-hand rule has to loop around the loop, and your thumb should point in the direction of the normal properly. But anyway, you add those together, and that gives you the dipole moment for this bent loop is simply iw squared rather, times y hat plus z hat. That is the dipole moment for this. So that's you know, it's nice to have a simple example after that monstrosity we just worked through, right? All right, so as the story was before, remember we had a physical dipole for the electric field, a charge q, a charge minus q, an actual distance between the physical dipole. And then if we got very far away from that, the far field approximation for it was the pure dipole, which we got from imagining the distance between the charges shrinks to zero, and the charge is basically the product of the charge times the distance is held fixed, even though the distance is going to zero. Somehow the charge is going to infinity in such a way that the product of q and d is held fixed. That was the ideal dipole. There's a similar story here in the sense that this is a pure dipole, right, which is not technically realizable with a current loop because you can't make a current loop that tiny to make that happen. But it's what you would achieve from shrinking the loop size to zero at the same time increasing the current such that the product of the area times the current is like fixed, even though the current's going to infinity and the area is going to zero. So it's a similar kind of story. And so here's roughly speaking the picture of a pure dipole. right, at the origin with the dipole moment pointing upward, something like this. Whereas this is a physical dipole, is a single current loop produces that, right? And there, that's more or less what it looks like. Now, if you get very far away from these two, they end up looking the same, right? Whatever, essentially, this particular local behavior of the dipole field gets washed away as you get far away. It behaves like the pure dipole in the far field approximation. And that's really the whole point of the multipole expansion, is to give us a concrete understanding of what's the far field approximation for systems. All right, that's what we're going to use it for later. Now here the dipole, again, this is a homework problem. You can rewrite the formula for the dipole just like this. If you go back and look at the formula for the electric dipole, it's the same formula, but with like, instead of, that's supposed to be a vector, I think, obviously, dot product with a, so back, it was p dot r hat minus p, I think, where p was the dipole moment for the electric field. So, but it's the same mathematics. It's the same same situation, right? Like the dipole potential is reciprocal with distance squared, and the dipole field is dependent on the cube of the distance. See that? It's got this 1 over r cubed here, and if you could look up there, there's the 1 over r squared for the dipole potential. And it was the same for the electric case, right? So there are some strong analogies that can be made here and can be exploited to solve problems if you're better at this stuff than I am. So that brings us, at last, to magnetic fields in matter. And so basically here's the story is like, well, how does magnetism work in the presence of stuff, right? So first of all, if you're a very critical thinker, and you listen to a physics professor blather on about magnetic fields and vector potentials and things, at some point you should grow impatient of why in the world have I not yet talked about magnets, right? Like, what does a magnet have to do with magnetism? Like, isn't that like kind of the whole point? And the answer is given to us in this next chapter, like chapter 6 in Griffiths, ultimately kind of explains what are magnets and how do they work. And I won't explain that entirely today. I'm just going to get us started. But it kind of depends on there are different kinds of material, right? So there's there's like paramagnetic. I think I'm missing an ick. My spelling is off. There's it's a paramagnet, a diamagnet. That doesn't feel right. Anyway, ferromagnet. I usually think of like paramagnetic, diamagnetic, ferromagnetic. I prefer to have those words, but I was in a hurry. Sorry, guys. But these are the three cases. So if the magnetization is like parallel to the magnetic field applied, that's a paramagnet. If the magnetization is opposite the magnetic field, and what is magnetization? Magnetization is dipole moment per unit volume, magnetic dipole moment per unit volume, just like before we talked about polarization being dipole moment per unit volume with respect to the electric field, all right? So here the story is a little bit more interesting. In the electric field case, pretty much we just had the polarization aligned with the electric field, right? Well, now, not the case necessarily. There's like different kinds of material that behave differently. Like I said, the paramagnet tends to align parallel. The diamagnetic tends to be opposite the magnetic field. And then there are ferromagnets, which you could make align any different which old way, but once you set it up that way and you take the magnetic field away, it'll stay the way that you'd aligned the stuff. Now, I say align the stuff. I'll talk more about that next class, all right? We can understand these different behaviors in terms of like some sort of story about the atomic arrangement of the materials and so forth. But as usual, the full story is given by quantum mechanics, so we only gain a little bit of insight. One of the main things, though, that's driving the whole discussion is the fact that we can have a torque on a current loop from a magnetic field, right? This is like one of the things we should really drive home in the introductory course is that magnetic fields put a torque on a current loop, right? But not a net force, because if you were to calculate IL cross B, so I goes this way, cross B, right? I cross B, so I get a force this way. If I go to the other one, I go I cross B, I get a force that way. So I got like force this way and that way equal but opposite. And if I, I cross into B, I get a force that way. Better not use left-hand rule, that's bad. I cross into B, I get force that way. So basically, you get opposing forces, and like that, right? And so if you look at the net force from the Lorentz force law on the current loop, you get 0. But if you look at how those forces are applied, if the loop can spin, obviously there's like a torque that's produced, right? Because, well, the forces like this don't produce a torque, but the ones that like this, they do produce a torque according to these formulas here, right? Like AF sine theta gives you the part of the force which is perpendicular to the radius arm here that it's spinning, and so we get this formula. Torque is the dipole moment across the magnetic field. All right, and so what this all means is that if you have material, right, and you apply a magnetic field to it, if we think about the electrons in the material forms some sort of regular solid, right? So the molecules are kind of stuck in place, and in that situation, as we apply the magnetic field, it torques, right? It twists the molecules and it tries to align them all in a certain way, and that ultimately leads to like currents being in the same pattern. And we'll talk about next time how that ultimately leads to a net dipole moment for the material collectively. All right. So, just giving you a sketch of it today. But what we're really interested in is the magnetization, which is the magnetic dipole moment per unit volume. All right. And so we just talked about how mu naught over 4 pi m cross r hat over r squared, that's the vector potential for a single dipole, right? So if you have a whole collection of them, you just take the continuous sum of that by superposition to get the vector potential, right? So if we integrate the magnetization across the separation unit vector divided by separation distance squared over the volume, that should give me the net vector potential. Now, a short calculation, which I'll show you guys next time, but this is directly analogous to, we did a calculation like this back in the polarization discussion, where we basically ripped the formula apart into 2 pieces, and then we labeled one part the bound charge density and the bound surface charge density, if you may recall this calculation. Very similar calculation allows you to rewrite that as the integral of 2 pieces, the bound current density and the bound surface current density. How do you find those? It turns out you get those simply from the curl of the magnetization or the cross product of the magnetization with the unit normal. All right? So there's bound current densities in a material with the magnetization, just like there's bound charge densities in a solid with polarization. So this is the analog. And so finally, that brings me to my final example for today, which is, well, what if we have a sphere, right, with a uniform magnetization, right? Now this sort of situation could be achieved by applying a strong magnetic field, for example, to like a ferromagnetic like iron ball or something. You apply a magnetic field to it, and a strong magnetic field, you could align all of the like molecular domains in the iron ball so that they're all pointing in the same direction. All right, that would give the iron ball a uniform magnetization like we're talking about here. And so it would look like that, like my picture. So, all right, well, what are the bound current densities in that situation? So the curl is 0, so there's no volume current densities, all right? But the surface current density of a uniformly magnetized sphere would be given by m cross r hat. But m is z. What's z hat cross r hat? Well, z hat cross r hat is phi hat times sine theta, as it turns out. And so, I mean, we could work that out if you guys like, but like this cross that is that. But hey, we've seen this before. In other words, hey, look at that. That's the problem we worked earlier. It took 4 pages, but we worked it out. Remember? The charge sphere. So it's like, it's basically the situation is that we've got m is equal to sigma omega r. So I need to go back and take my example 1 and replace sigma omega r with m. And if we do that, we'll obtain that the magnetic field within the sphere, uniformly magnetized sphere, the magnetic field is uniform. And it's in the direction of the magnetization, and it's actually 2/3 mu naught times the magnetization. Just like that. And then, of course, if you go outside the sphere, what it's like is it's as if you have a single pure dipole at the origin, with the value of that dipole being 4/3 pi r cubed times m. So that's like, this is dipole moment per unit volume. So if the total volume is 4/3 pi r cubed, this gives me the total magnetic dipole of the uniformly uniformly magnetized sphere. Now, if we go back to my previous example, like, let's do that for a second. You guys remember for me, sigma omega r equals to m. Repeat after me. Sigma omega r equals to m. Sigma omega r equals to m. Sigma omega r equals to m. So this just becomes m vector. So we have 2/3 mu naught m vector is the magnetic field, like I said. I don't know, I'm very happy actually that I didn't do the example last class, because I wanted these 2 examples to be in the same class, even though they're in different chapters, because this, the final example today, I was like, whoa, that's really cool. And also, this is exactly what happened, pretty much, with the uniformly polarized sphere in electrostatics. There we also found that the electric field was constant within the sphere and proportional to the polarization, I think. And then outside, it was as if there was a single dipole at the origin, and it was just the dipole field outside. Same thing here. There's some constants which are slightly off, but the story remains the same. So anyway, next time I will explain more about how it is that we can think about the magnetization of an object as a consequence of superposition across atomic domains, essentially, as a sort of heuristic explanation, with the understanding, of course, that we are glossing over quantum mechanics, because the spin of electrons actually is part of the story, and that's an intrinsically quantum mechanical kind of thing. The spin of an electron is something intrinsic. It actually has nothing to do with any kind of spinning motion or anything like that, as far as we know. It is a fundamentally basic thing. It's like mass or charge. It's just something particles have. It's not something, as far as we know, that's a consequence of some sort of dynamical behavior of the particle. So the word spin is actually kind of a poor word for it. Maybe we should say the magnetization of the electron or something. That might be a better thing to call it, because it pretty much describes how the electron couples with a magnetic field. That's what spin does. But anyway, I shut up. See you guys next time.